Hello all. In this video, this is the last week, and in this video I'm going to do some review, and after that probably we will close this course, and I'll just do how this course panned out. I'll give you some 30,000 feet overview, some basic ideas, and then what kind of questions you can expect in the exams. So, and with that, I will close this exam, course. So today, this is the review. So this course is all about predictive analytics, predictive analytics, regression and classification, correct? So in some sense, in machine learning literature, this entire thing comes into the supervised learning. Okay, so this is just a matter of the classification in statistics. Statistics literature, we call it regression classification, whereas this is more statistics jargon, whereas supervised learning is more ML jargon, with slightly different approach. Both methods, both technique have two objective: inference and prediction. Now, statistics community historically focus more on the inference, and ML community, computer science community, historically focus more on the prediction. Okay. So the thing that I would recommend that you should, I would not say that ML community only focus on prediction, but majorly ML algorithms, ML approaches are mostly focusing on prediction, like as accurate as possible prediction, whereas inference is not. But nowadays they are also getting conscious about doing correct kind of inference, whereas statistics community historically more focus on the inference. Of course, instant community also wants to do good prediction. It's not like we don't want to do good prediction, but it's historically focuses on the inference. When I'm saying inference, that means we want to say something about more causal kind of remark, or maybe is there an association after taking care of the variability for other predictors and stuff like that. So this is something we want to speak about. So typically a problem in predictive analytics will have a Y, a response variable, okay, response variable. It could be many things. It could be continuous, it could be binary variable, and it could be count. Generally, these are the three type of variable you will find. Now, typically, if it is continuous variable, then typical distributions that we think of: Gaussian, gamma, log normal or log Gaussian, etc. If it is binary, mostly we do either Bernoulli or binomial. Binary, Bernoulli or binomial. And if it is count, then generally the distributions are Poisson, negative binomial, okay. And there is a fourth case, K-level class problem, K-level classes, K-level ordinal variable. Okay, for if it is binary, then means either it is yes, no, but there could be three-level problem, right? Like we have seen in Fisher's iris data set, there are three different species. It's not binary species, there are three different species. In this case, the distributions are popularly known as multinomial. This one case we have not covered in this course, but in future I would like to cover in this course or in some advanced course. All right. Now once you have this, you will have bunch of features. You have bunch of features, right? x1, x2, ... xp. So the data set that you will have typically bunch of y. Typical if you have an Excel kind of format, Excel kind of data set, you have one ID, bunch of ID, 1, 2, 3 up to n. Then you have bunch of x1, x2, xp. So this is like x11, x1p, x21, x2p, xn1 ... xnp. And then you have y, which is y1, y2, yp, yn. So this is typical Excel. You can think of an Excel kind of structure that you have. So you have first row IDs and then bunch of columns and then response. Now you can write the y column as n cross 1 x beta plus epsilon. We have discussed about it. We discussed Ols estimation, which gives us, if we define sum of squares of delta y minus x beta transpose y minus x beta, then we minimize that, and the Ols estimator gives us beta hat as, first normal equation, first it will give us normal equation, right? First it will give us normal equations, which is x transpose x beta x transpose y. And if you solve this, it will give you beta x transpose x inverse x transpose y. So this is our least square estimator, LS estimator. Correct? Now in this LS estimator, if we assume our epsilons, these epsilons follow normal 0 sigma square, then what happens is we can show that this LS estimator follow normal beta sigma square x transpose x inverse. So from this, what we can do, we can estimate, and we can estimate the sigma square using residual sum of square. So from here, so this is the sampling distribution of coefficient. This is the sampling distribution of coefficient. Okay. So this is the sampling distribution of coefficients. Now, once we have the sampling distribution of coefficient, we can do the statistical inference using beta hat plus minus z times s. Now, what is s? S is effectively the or beta I hat is z times si. Now, what is si? Si is effectively sigma hat x transpose x inverse the ith element and then square root sigma square this, the entire thing square root will be the ith. So basically this will be sigma square x transpose x inverse will be a matrix of P cross P. We will take the ith row, ith column, that this item will be our Si, and from there we can do the estimates and do the statistical inference. Now, how we do the statistical inference? We want to check whether a particular ith element beta I equal to 0 versus beta I alternative hypothesis that beta I not equal to 0. And of course, if zi is absolute value of zi is greater than some cutoff value by 2 or something, we will reject the null hypothesis. So this is typically the way we do it. Then we did stepwise selection. We then talked about stepwise selection, right? So there are, in y you have beta 1 x1 plus beta 2 x2 plus dot 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 beta p xp plus epsilon. Now there are p many features in your model, right? You don't want to choose all of them. You want to drop some of the features which are effectively useless. You want to come up with a much more smaller model, right? So how many models you want to drop some, you want to keep some, you want to bring it back or something like that. All kind of permutation combinations of models you want to try, and based on that you want to choose the best model. So how many models you can try out? So if you do a best subset selection, you want to do all possible combination best subset selection. Then, so in the base subset selection, you have 2 to the power p minus 1 many models you have to consider, correct? You have to consider that many models, and so it is kind of impossible beyond say 10 or 12 features. Now what you can do, instead of using base subset selection, you can try forward or backward subset selection. Okay, in this case, that I'm not going to the detail of the algorithms. I have done that in the previous videos, in the previous weeks. So you have to choose effectively P models, and out of P models, P choose 2 is the sort of a, so it is like P into P minus 1 many by 2 many models you have to choose. So which is much order of P square, so much better handle, you can handle it much better. So this is something you should try out, think about. Then one of the issue that we have discussed is multicollinearity in the data. Multicollinearity. Now what happens in the multicollinearity if two, say if you have a model beta naught plus beta 1 x1 plus beta 2 x2 plus epsilon. Now if x1 and x2 they are highly correlated, okay, strongly correlated, okay, so O is high, correct. Now if this x1 and x2 is very high, the correlation between these variables are very high, then what happens, essentially the if coefficient estimation becomes very difficult, because now in the Ols estimator you have to invert this design matrix X transpose X, and now since they are highly correlated, they become ill-conditioned. This becomes, so basically X transpose X becomes ill-conditioned, right? You become ill-conditioned, so multicollinearity becomes a big problem. You cannot, the margin of error becomes too large. You get some estimations, but they are unreliable. Margin of error are too large, so you get, so the estimates of beta becomes unreliable, okay. Now in this case what you do, you use ridge regression. In this case you use ridge regression, and what we found in this case is we can something called ill-posed problem. These are all called ill-posed problems, and in these ill-posed problems we can solve it by putting a penalty term. So our delta was, we defined y equal to y minus x beta transpose y minus x beta. Now what you do, you put a penalty term on this. This will be called L2 penalty. This is called L2 penalty. Or you can do delta equal to y minus x beta transpose y minus x beta plus lambda mod beta. This is typically called L1 penalty. And then what you do, you solve it as an optimization problem. Solve it as optimization problem. So in this case you will give reach, and in this case you will get lasso solution. Lasso solution, what happens, it does a variable selection technique as a variable selection, because what it will do, it will, some of the betas will go directly to 0. As those beta will go directly to 0, you will automatically, that means those predictor does not have any effect, so you will throw them out, right? So this is an interesting phenomena that we got. Then obviously we studied the basis expansion. How can we do that? So feature engineering is another thing. Feature engineering and basis expansion. Feature engineering and basis expansion we spoke about. So basically you have y and x, and suppose this is the data that you have, and you think like no, y equal to alpha plus or beta naught plus beta 1 x plus epsilon. This is the model you want to fit, but now you are thinking maybe I will put a quadratic term, beta 1 x plus beta 2 x square plus epsilon. That means essentially you add a new dimension in your data. Now your data are not in 2-dimension, data are in the 3-dimension, and you are not fitting a straight line, you are now fitting a hyperplane. Now you are fitting a hyperplane through those data. So in 3-dimension you are fitting a hyperplane, but those hyperplane actually fitting in 2-dimension. You are projecting, when you project this fitted model, it will fit some sort of something like this. When this hyperplane, when it gets projected, the way it will take the shape, it will get projected in the lower dimension, it will fit like a quadratic function. So a quadratic function in a higher dimension is a hyperplane. So that's an interesting phenomena that we found, and so that means linear functions are not, linear models are not linear in variable, they are linear in parameter. Remember that. They are linear in parameter. Okay. Next, so you can expand as many as possible, but as you do more and more feature engineering, the model complexity goes up. Higher feature engineering, more feature engineering means higher model complexity. Let me just erase this. More feature engineering means higher model complexity. Now, in this case, what you can do is, as the feature engineerings are, you are adding more feature engineering will probably help you increasing accuracy, but it might result into overfitting. So too complex model may lead to overfitting. Now, what is overfitting? Overfitting means in a new test data point, it will, or bunch of test data points, it will do very bad. Your accuracy will be really on the floor, like, it's really bad. It's really bad. So you have to be somewhere struck the balance. You have to be careful on that, and variable selection can help you out with that. Next, obviously, we studied, what happened with the homoscedasticity, the model, checking the model assumptions, checking the model assumptions. Model assumptions like homoscedasticity, then homoscedasticity, then Gaussianity, whether the residuals are correlated or not, So all these things correlated, autocorrelated or not. So all these things we have checked. So you must do the check at least on the final model which you will finalize. On that you do the model assumptions checking. If the Gaussianity does not hold good, you may go for, if Gaussianity fails, I recommend go for bootstrap. If other things fails, then probably sometimes you have to just leave with the whatever model you have. But if the assumptions fails, that indicates that most likely your model does not explain many things. All right, next is you have if you have we went to classification. So the classification is, we did logistic regression with logit link and probit link. We checked how nonlinearity and non-monotonicity of under the logit link or logistic regression, non-linearity, because in logistic regression pretty much everything non-linear, so you can't really expect linearity except in the latent space. So what you expect is non-monotonicity. We have also learned to model non-monotonicity. Okay, then we did discriminant analysis. We discussed, at least theoretically, what is the neural network. Then, so we discussed all these things: discriminant analysis, neural network, decision tree, and random forest. We also compared logistic regression and discriminant analysis, all these models, and in German credit score data and many other data. German credit score data, then fake banknote data, fake banknote data, then genetic data. So we did discuss all these things, and then we find that if you do carefully feature engineering the logistic regression, then logistic regression also becomes sometimes as good as neural network or decision tree or random forest. And that is one of the reason logistic regression is still very popular, because one of the reason is in logistic regression is very easy to explain compared to some of the very complex model like random forest. Decision tree is reasonably okay, but neural network, random forest, those things are a bit difficult. Discriminant analysis is also very reasonable. So my suggestion is you try all the things, and in some data you will see some model is doing good and another model is doing good, and it's a bit difficult. It also depends on your objective, what you want to do. Then we discussed Poisson regression with respect to English Premier League football data, EPL, English Premier League football data. Okay, and we we applied all kind of, stepwise selections, and we tried to come up with, we also did we did all these analysis with R, Python, Julia, and I discussed at the end the last week that why Julia. I started my career with R, then I moved to Python. For last 5 years I'm doing Python as well, but nowadays for last about a year I am moving to Julia, and I really think this language is very good language, and eventually many data science projects will eventually move to Julia. So I think it's a good time. If you're learning a new language, it is better you start with Julia. And if you want to learn only one language, but yeah, I really like this language. So what, I will stop here, but before I stop here, I want to tell you that you, for the exams, final exam, you guys focus on the assignments. Definitely do as much as assignments, all those assignments, revise those. Definitely look into my lecture notes, and all the discussions that we have done, and so you can expect pretty much whatever I have discussed, things will come from there. And good luck guys, and in the next video I will conclude this course. Thank you very much. Take care. Bye.